Okay, question 3 on this AP Stats practice test. This is another one of those questions that ideally you'd be able to answer in like less than a minute on your test. The topic that this deals with is the shapes of distributions. And the idea is to look at the histogram and tell which of the following shapes it looks the most like. The 4 standard shapes that you should be familiar with are these 4 down here. The first one that I listed is the normal distribution. The last one that I listed is the uniform distribution. And the middle 2 are left and right skewed. I think the most common mistake people make is confusing the 2 of those. This distribution, where most of the observations are over on the left, surprisingly is called a right skewed distribution. And this one, where most of the observations on the right, is called a left skewed distribution. One way that you can remember these 2 is think about the tail. In a right skewed distribution, the tail is over on the right side. In a left skewed distribution, the tail is over on the left side. So to figure out the shape of the distribution represented by this histogram, all you're supposed to do is look at this and ask yourself the question, which of these 4 does it look the most like? Well, I'd argue that it looks the most like this one. Most of our observations are over here on the right side, but we have this tail going down to the left side. This distribution is left skewed or skewed to the left. The answer to the question is B. Maybe it's easier to see if you kind of transpose this on top of the histogram. You get something that kind of looks like this. This is definitely a left skewed distribution. You might notice that I only talked about 4 of these 5 answers. I completely ignored the chi-square distribution. The reason why is because this doesn't have one given shape. There's lots of different chi-square distributions depending on the degrees of freedom. I think the minimum that you should know going into your test about the shape of a chi-square distribution is that depending on the degrees of freedom, it's anywhere from right skewed to normal. For that reason, they can't really even ask you a question where the shape up here is normal, and these are your 5 options, because a student could argue that it's either normal or a normal looking chi-square. Similarly, they can't even give you one that's right skewed, because again, a student could argue that the correct answer could be right skewed, or it could be a chi-square distribution that looks right skewed. So really, in order to make this a fair test question, the only possible answer is left skewed or uniform. In a uniform distribution, all of the bars have roughly the same height, which is certainly not the case here. So even without knowing what a left skewed distribution is, I guess you could process of elimination your way into this answer. But it's definitely easier just to know what the distribution looks like. In addition to knowing these shapes, it would be good if you were comfortable with what a box plot would look like for at least these first 3. For the normal distribution, most of your observations are in the middle, loosely speaking. The median is roughly halfway between the first and third quartiles, and the lines extend out into the tails. We have some nice symmetry going on. The box plot looks, loosely speaking, like this. In a right skewed distribution, most of the observations are over on the left. So we draw our box over here. We have a very short tail to the left, but a long tail to the right. A good fact about right skewed box plots is generally the median will be closer to the first quartile than the third quartile. So I'll draw it over here. A left skewed box plot is essentially the reflection of this guy. My big tail points out to the left. Most of my observations are over on the right. I have a really short tail to the right, and my median is closer to my third quartile than it is to my first quartile. Finally, the uniform distribution. I don't even think it would be fair to ask a student to distinguish between a uniform and a normal box plot because their shapes are so similar. But just in case you are asked, the idea with the uniform box plot is it looks very similar to the normal box plot in that we have most of the observations in the middle and this nice symmetry going on. The difference is the tails don't extend as far. And the way you can kind of remember that is that in the uniform distribution, you're equally likely to get any value within the bounds of the distribution. So roughly a quarter of the observations will be to the left of some point that's a quarter of the way through this box. Roughly half the observations will be to the left of a point that's halfway through this box. 3/4 of the box. What I'm saying is this distance should be roughly the same as this distance, roughly the same as this distance, roughly the same as this distance. That's certainly not the case in a normal distribution where these lines are significantly longer than the distance from the median to the first or third quartile. Maybe I didn't do a great job of drawing this. I really wanted to emphasize these short lines as that's the difference between these 2. But these lines should be about this long, whatever that distance is. Anyways, back to the chi-square distribution. As I mentioned before, the minimum you should know about it is this fact. But I think it'd be useful if you understood why this was the case, not necessarily for this problem, but for similar problems. So let me talk a little bit about the chi-square distribution. The way to think about the chi-square distribution is to think about the squares of observations from a standard normal. And you might be like, well, that doesn't help me at all. There's a lot of statistical jargon going on in there. It's not as bad as it seems. So when we talk about a standard normal, I'm just going to draw a regular normal distribution. Sure, that's good enough. But what makes it standard is the mean is 0 and the standard deviation is 1. So we got something like this. Think about randomly getting an observation from this distribution, right? You'd expect it to be pretty close to 0 because that's where the curve is at its highest. But you wouldn't be surprised if you got a 1 or even a 2 or a -1 or something. Whatever, you get an observation, but then you don't stop there, you square it. So if you drew 0, 0 squared is 0. If you drew -1, -1 squared is +1. If you drew 1/2, 1/2 squared is 1/4. Now think about if you created a curve like this that tracked all those different values. The first observation is that this thing would never be negative, right? Because if I end up pulling a negative number from here, when I square it, it becomes positive. So the smallest things we'll ever get is 0. The other observation is that I can get fairly large numbers out of here. Right? It's pretty unlikely that I'll get anything bigger than like 3 out of this guy. But since I'm squaring whatever I get out of this guy, if I did get a 3, or a -3 for that matter, when I square it, that turns into a 9 over here. So if I keep my scales the same, all of a sudden this has to be way longer than this one was. Now what's my curve going to look like? Well, odds are I get something pretty close to the middle, right? Something between -1 and +1. If you're familiar with the empirical rule, you might know that there's a 68% chance that I pull a value between -1 and +1. If I pull any value between -1 and +1 and square it, I'm going to end up with a value that's between 0 and 1 over here. So all of that area between -1 and +1 has to fit over here between 0 and 1. However, if I end up with the value between 1 and 2, or -1 and -2, when I square those values, I'm going to end up with something between 1 and 4. I guess 4 is right here. So it's not as likely that I'll end up in this range, but it's still certainly possible. What I'm getting at is most of the observations are going to be over here. My curve's going to be really high over here, but I'm going to have this big tail going out to the right to account for the fact that it's reasonably possible to get values close to 3 over here, which would transform into values close to 9 over here. There's my curve. Hopefully when you look at this, you realize that a histogram representing this would look pretty damn similar to a histogram representing this, right? You're gonna have the tall bars over on the left side and this big tail going out to the right. So you're like, wait, chi-square distribution just looks the same as a right-skewed distribution? Not quite. What I drew for you here is the chi-square distribution with 1 degree of freedom. The degrees of freedom in the chi-square distribution refer to how many observations you pull over here. So I just took 1 observation from over here and then squared it. But what if instead I took 2 observations from over here, squared them both, and then added them up? Well, I won't go through the whole derivation, but maybe you'd believe that what you'd end up with would look something like this. It's not a great picture, but I think it captures the general idea. When I pull something from over here and square it, I'm guaranteed to get a positive number. However, now I'm not done when I just pull 1 of these numbers. Now I'm going to pull 2 of these numbers. So it's still fairly likely that they'll both be close to 0. And so I'll square these 2 small numbers, which will result in 2 small numbers that I add up and still get a small number. I still want my curve to be highest over here at 0. But the tail is getting a little bit fatter because now I have 2 chances to pull a larger number, or pull 2 medium numbers and add up those squares to end up with a larger number. If I have 2 degrees of freedom, I get something that looks more like what you see in purple. And we don't have to stop with 2 degrees of freedom. I'll draw one more for you. If you had 3 degrees of freedom, now we have 3 different observations over here that we're pulling and then squaring and then adding up. And it turns out that's kind of the tipping point. With 3 degrees of freedom, my graph looks more like this. My tail's getting even larger. And note that it's getting less and less likely that I end up with the sum really close to 0. Because even though each observation individually I expect to be pretty close to 0, when I square that observation and add it 3 different times, I'm starting to expect that sum to be a little bit bigger. I don't want to try to draw more chi-squared distributions with different degrees of freedom, but I want to impress upon you the fact that there's not just one probability density function for the chi-squared distribution. The normal PDF always looks like this thing. The chi-squared one, well, it depends on your number of degrees of freedom. Let me show you some better pictures of the chi-squared distribution. Wikipedia does a good job on this. Pictured in this ugly yellowish green color is the chi-squared distribution with 1 degree of freedom. We expect a value pretty close to 0 because there's a pretty good chance that the standard normal value that we draw will be between 0 and 1. And when we square a number between 0 and 1, we get a number between 0 and 1. That's why this graph is so high between 0 and 1. As we move on to 2 degrees of freedom, we see a bigger tail in green here than this like pea green color here. And as we continue to add degrees of freedom, the shape of our curve changes over and over and over again. Note that when we have 9 degrees of freedom, I wish this graph weren't cut off, what we end up with here starts to look more like a normal distribution. That's a really interesting fact. I could spend a lot of time talking about why that is, but this video is already pretty long, so maybe I'll just leave that as a comment. As the degrees of freedom increases, your graph becomes less right skewed and more normal. Again, at a minimum, have this fact memorized, but I think what would serve you even better is to kind of understand why. If you can understand the chi-squared distribution in terms of the standard normal, I think that would give you a big leg up in this test and give you knowledge that most test takers frankly wouldn't have. However, all of that was way beyond the scope of this question. For the purposes of this question, really all you needed was to have memorized these 4 different shapes and kind of ignore answer D as a possibility.